Welcome back to COS 217 lecture. We talked about testing last week, and when you design a testing suite, you might try to anticipate the ways in which a program can break. So you write some tests, and then you find that your code does fail on one of them. Great! That means if you did a thorough job in test design, you know exactly the situation that you were trying to catch, and so you have some head start on finding the bug. But even when you experience a failure that was not planned for, debugging requires a similar intuition of trying to root out the underlying causes of these failures. So now let's take a look at some structured approaches to finding the bugs that cause those failures, and also some heuristics when we don't have a perfectly good structure. So as programs get larger, there's more that can go wrong in a number of different ways. There's a larger code base. That means simply more lines of code, so more chances of a typo or conflating two variables or anything like that. A larger code base also likely means that there's more interconnected pieces and more complicated interfaces, so there are more places for a contract to be broken or a handoff to be botched. As you begin to work with larger programs then, you'll need more advanced skills in debugging to fix the problems that crop up as you deal with larger software systems. That said, debugging is at least as much art as science, and there's a fair bit of experience in building the intuition that goes into effective debugging. So in this lecture, I hope to give you some heuristics and simple approaches to employ that, by their very use, you'll be able to gain some of the experience. This lecture may appear quite short at first, and indeed it's only a little more than a dozen relatively high-level suggestions here. But there are a bunch of examples of buggy functions and programs on this slide, and so while it would be easy to just look quickly at the code, ignore the pause icon, and then listen to my discussion, I frankly don't think you get all that much out of it. This isn't a lecture to be watched passively. Instead, I suggest that you pause the video each time the pause icon shows up in place of my face, and figure out what the problem is, and announce your answer in 4 parts. What is the problematic piece of code? In which cases does the problem present itself, since most bugs aren't always wrong, just under some conditions? What is the effect of that situation that's erroneous? How does the bug manifest? How can you see it? And finally, how could you fix the bug? So don't be misled by the video runtime. If you really engage in the slides, it will take considerably more time to get through. So with that warning proclaimed, let's get to it. The first technique seems obvious at first. When you get an error message, you should understand it. But some error messages can be rather opaque, and some can be even completely spurious. Before we can even run a program and fail a test, we have to be able to build the program. But that's the first place that we can get evidence of an error in our program. If the build process results in errors or warnings, the error might indicate that it's not a valid C program, or a warning indicating that they suspect we might have a problem, but can't guarantee it. Here's our first bug hunt. Take a look at what errors you might find in this program. Then we'll see what GCC 217 has to say, and if we can understand what it's telling us. GCC 217 reports that there is a fatal error that crashed the build process. What does the error mean, and which stage of the build process triggered it? The preprocessor reported the error that a certain file we tried to pound include doesn't exist. We correct the typo and try again. Here's the fix. With the comma in standard I/O replaced with the required period. But what does GCC 217 say now? GCC 217 reports on an error near and dear to your heart at this point. From assignment 1, we know that the preprocessor is responsible for decommenting, and it will report an unterminated comment if it discovers one. So we add the */ to terminate the comment, and what does GCC 217 say now? GCC 217 reports two issues. Number one, an error on line 6 that there should be a semicolon before the return statement. And number two, a warning that control reaches the end of a function that should be returning a type. So take all that in. What stage of the build process is reporting these errors? What's wrong on line 6? And why does control reach the end of the function on line 7 without a return when return is sitting right there on line 6? Here the compiler reports the issue with the missing semicolon, and it's right about the problem, but it reports it in a way that can cause confusion and delay in debugging. The line number is off by 1 because the compiler only notices the issue when seeing the return keyword, not at the new line, since we can stretch lines of C code over multiple lines. And the warning is actually a red herring entirely. We do return, it's just that the prior error corrupts that return by confusing the compiler that this was one long line. Fixing the semicolon makes both of these go away. Let's reset and see the program again with all those errors fixed, but a new one injected. Take a look at the program and try to spot the error. Then we'll see what GCC 217 says and if we can understand what it's telling us. GCC reports a warning and an error. What stage of the build process is reporting these, and what do they mean? The bug is that we've misspelled printf. The compiler reports a warning. It's cryptic at first, but it does give the required information if we learn that implicit declaration means you didn't give a declaration of this, nor did any header file you included, but that doesn't mean it doesn't exist, so I'm just going to tell you that you might be off on the wrong track, but who knows, maybe the linker will find something. And it is nice enough to point us directly to the identifier that's the problem, so we can read it again for ourselves if it is in fact an issue. The error comes from the linker. The linker responds to this warning from the compiler and says, no, it doesn't actually exist anywhere I could find. I give up. Your build is dead. And again, it tells us the exact identifier that it can't find. Let's reset the program one more time with that error fixed, but a new, particularly tricky one injected. Do you see the error? We've again misspelled printf, but this time instead of omitting the I, we've replaced it with a dotless I as found in various Turkic alphabets. This one wasn't quite fair because while GCC using Clang on my MacBook does result in the exact same error as the other misspelled printf, on ArmLab GCC throws off errors for stray bytes because the program tries to parse the printf identifier that contains a Unicode character. But let that just serve as a reminder that C source code isn't portable. Alright, one last build time bug. See if you can find the issue. Alright, let's see what GCC 217 says. The compiler catches the error, but doesn't really provide you much help in fixing it. What does this error even mean? Well, in this case, it's a common bugaboo with enums. We have to close them with a semicolon. Sometimes the error messages tell you nothing more than the general area where the error resides. But there is a useful tip for the inscrutable errors about what the program was expecting. Oftentimes, this is indicative of just, you have a syntax error, as the compiler can't figure out what you're trying to do. So if you see something was expected, that's normally a syntax error, and it'll point you in the right direction. But again, not necessarily very clearly. So it is definitely worthwhile to become familiar with common error messages, but it's nigh impossible to know them all, and unfortunately, sometimes error messages aren't helpful. Perversely, the error messages for obvious things are often better than the error messages for tricky things. Two more quick tips here. You should use your editor's AutoIndent, for example, Control-XP in our Emacs setup. This can catch missing punctuation that causes syntax errors, we just saw confusing error messages, because it will look wrong. The code will look wrong. It will misindent because of the syntax error. The second thing, as we saw above, is we should fix one error at a time. Some later errors may go away because they were figments of a previous one. The second tip in debugging is to think before writing new code or changing existing code to fix a bug. This seems obvious, and yet many times students get stuck and start changing their code in undisciplined ways. And frankly, 126 somewhat exacerbates this. Make a random change, see if more or fewer Tiger file tests fail. Those of you who have taken 226 will remember how hard a habit this was to break. Unfortunately, many times this haphazard changing of code takes you much further from the correct solution, rather than even more so than the original was. So think before changing your code. It's often helpful to explain your code, or even read it line by line out loud. This can be to yourself or to someone else, and the listener doesn't even have to be able to help you. A younger sibling, your humanities roommate, or a stuffed animal will work just fine. It's really just about hearing the code and noticing the error that your eyes have glazed over so many times. If it doesn't jump out at you, it's reasonable and proper to experiment with changing the code, but make sure your experiments are disciplined. Think, develop a theory, change your code to test the theory. Don't just change your code to see if it works. If you find yourself diving into undisciplined changes, stop and seek help. Doing so is a sign of a deeper lack of understanding, that you're not able to formulate a correct theory as to what could be wrong. In number 1, there were some common error messages that you might want to learn to remember their association with the bug. A more general case of this is knowing what bugs are common in the first place, and seeing if you've fallen into one of the traps set by them. Let's take a look at some of these office hours frequent flyers. Again, pause the video and assess what is the error, how does it manifest, and when, and how would you fix it. So super common errors in this class include accidental fall through for switch statements from one case to the next when there's no break. Missing the ampersand, the address of operator, when making a pointer out of a different type, especially in functions like scanf. Declaring too small a variable for the function's return type. This is especially problematic with getchar, where EOF is an integer value. Feeling like you're too cool for parentheses, or that they make your code ugly in some way, and then falling into an incorrect precedence or associativity issue. Mixing up assignments and logical equals, especially in a conditional where it wouldn't compile in Java, but does in C. And similarly, mixing up logical and bitwise operators in a conditional. This wouldn't compile in Java, but does in C. And again, similarly, in that it's illegal in Java but legal in C, the inequality chains. These almost certainly don't do what you think they do. In this case, 5 is less than I is less than 10 computes either true or false, 1 or 0, for 5 is less than I, and then compares to 10. But both true, 1, and false, 0, are less than 10, so this will always result in true. Do note that the compiler will generate some of these, generate warnings for some of these bugs when given the -wall option. So in some cases, the compiler can help us out. But again, it is definitely a more permissive language than Java, and this can lead you down some dangerous roads. All right, so each of these nested loops also has an issue. Pause the video and find them. The error in the first example is that the inner loop increments I, not j. And in the second example, the inner loop increments j rather than decrementing it. These are heuristic errors, where the brain sees the parts as inextricable from the whole. But the brain is frighteningly good at seeing patterns and ignoring details, so it thinks it recognizes the whole, even when it's wrong. Experienced programmers might even be more prone to this than novices, because their brains are more tuned to these patterns, so they're more likely to overlook these simple bugs. Note that these bugs come about most often when copying and pasting code, so be careful about that. One last common error that is particularly prone to trip up Java programmers. Pause the video and see if you can find it. In Java, this is an error. Java-C will explain that I is already defined in this function, main. C, though, is permissive with respect to block scoping. So in C, one local variable can shadow another, just like in Java how a local variable can shadow a instance variable. Thus, in this case, the printf will print 5, not 6. You'll see more about scope, duration, and visibility in precept 14. Your fourth technique is divide and conquer, which certainly doesn't mean just hand off your program to somebody else to help you with it. It doesn't make sense to keep banging your head against a huge example that fails. It's almost always worth the effort to come up with a simpler example, a smaller example that also fails. It's easier to wrap your own head around it for manual inspection. It's easier to step through it with a debugger, and it's easier for a lab TA or preceptor to get up to speed when trying to help you. We'll always be happier to help you in office hours if you can show us a few character input that causes a bug rather than a gigabyte of randomly generated goop. If you're already failing a case, try cutting it down. The end of that case might not be the issue. If you cut it down more and more, you'll eventually come to a point where the input ceases to fail. And that last change is the problem point. You can examine the contents of that last bit to see what parts of your code they exercise. That can give you a direction to chase off for on your bug hunt. Similarly, you might start with a very simple test case that succeeds and keep adding to it until it fails. Again, the last bit added is your problem spot. You can take the same approach to the code itself. If you have a big hairy test client that's failing, you might have no idea where the bug is in your module. But if you comment out calls to various functions, eventually you'll find that your bug disappears. The thing that you just commented out is likely the source of your problem. That is, you've isolated where to go search for your bug. Do, though, be sure to keep the code that you remove. That's why you should comment it out or somehow inactivate it, maybe with an if zero. You do still want this code. You just want to figure out what you're doing wrong with it. And going the other way, you might want to start with a minuscule, trivial little test client and build up with more and more test content until a problem reveals itself. This is perhaps more natural while doing the initial development, where you're writing functions one at a time, whereas the remove process is more common once you have a mostly working program and you've started to expand out to real-world tests or larger test clients. We can extend the idea of divide and conquer, but rather than changes to the input, we can take the same tack for changes to the program's code itself. Focus on recent code has two meanings. First, it means focus your effort on recent changes. Test and debug as you go. And second, focus your bug hunt on recent changes. If something's broken, look first at the last thing you did. This is the principle of regression testing, but it's only effective and feasible if you follow number one, because otherwise you have no assurance that it worked before. It's also tempting to think, my current version isn't really what I want. It's not working right now, or it isn't what we need, and so there's no point backing it up before I start off and making changes that are needed. It's also tempting to think, I'm going to make this change and everything will work fine. Both of these mindsets risk losing code that you know it's status quo. Maybe it doesn't have all the features you need, maybe it has a known bug, but you know what's what with it, and that's valuable. Losing it and then progressing on and getting into a situation where you're not sure what's in your code now, what's changed and what hasn't, etc., just makes for extra debugging and more second guessing. As frustrating as it might be to check in code that you know isn't right, and you know that's going to get changed imminently, it's valuable to do so, at least in a developmental or feature branch, maybe not into main. Because if you walk into a maze of new changes and can't figure out up from down or how to get yourself back out, you can always time travel back to before you made these changes and start anew. Or more reasonably, instead of completely starting over, you get to at least cross-reference your current status with the previously well-known state to get a clear sense of what has or hasn't changed. We used to suggest in this class that every time you started a new section of a project, you copy your project directory over into a new directory whose name included a timestamp. This is now decidedly not what we recommend. Instead, you should be using your Git repository, which does all that and more and does it better. I was thrilled to see in Assignment 2 Office Hours that a lot of people have really great setups where their IDE automatically checks in and pushes changes for them, or others had the manual edit, commit, push, pull sequencing down to a science. This is great and you should keep it up. I heard a couple of people saying that the lab TAs were harassing them saying, oh, come on, just transfer the files, you don't need to check in. You're doing the right thing. You can ignore them in this case. Even though they give good debugging advice, they're not necessarily great software engineers. All right, number 6 is a quick one. If you're failing test cases, sometimes the answer is actually to add more tests. As we saw in the testing lecture, internal tests can help you to find bugs. And so if we create more and more of them, we might be able to zoom in on exactly where that bug is occurring, rather than just a higher level test telling us that a problem exists in general. And in addition to actively isolating where bugs may be, internal testing can also passively eliminate entire sections of our code from having to search in the first place. Because if the bug was there, it would have tripped up our internal invariant testing or parameter validation. All right, I hesitate to go here because it's the status quo for many beginning debuggers, and I'd like to be moving away from it. But nevertheless, there is indeed great deductive power in a small set of precision-targeted printfs. It's a very 126 way of doing things, but it is valid for small cases to determine where the problem first manifests, or if it's already apparent where it is, what exactly is happening to one particular value. Note, though, that there are some tricky bits with printf debugging. And that is, one of them is buffering. Standard out stream buffers. That is, it doesn't immediately print to the terminal what you call printf on. It'll keep it in a buffer in memory for a little bit, so it can print it all at once in bigger chunks to be more efficient. This means that if something has been printf'd, but is sitting in a buffer and the program crashes, the program could crash before the output appears. This doesn't do you very much good if you've been doing printf statements like, I got here, I am here, got to this line. We can flush the buffer when printing to the terminal by just putting a new line character into the stream, but this doesn't help if we're redirecting to a file. The better way to print to standard out and enforce determinism about whether we have actually printed out, in reality, or if it's still sitting in a buffer, is to dofflush, which explicitly flushes the stream. Another option is to use standard error instead of standard out. This is advantageous because our programs tend to print to standard output, and so if we do our debugging output on standard error, we can separate it from standard out, so it's not all mixed together. Even better, standard error is unbuffered. We could also print to a file explicitly instead of just printing to one of the standard streams and redirecting. The log file approach is actually used frequently, especially by long-running programs, because it's helpful to find bugs that don't appear until after, for instance, a loop is executed for a lot of times. It also provides a persistent record of a bug, so you don't have to catch it live. As an alternative to displaying output to the terminal or to a file, you can use a debugger. This gives you a more targeted interaction with your program's state. You can see exactly what's in memory, when, and where, and what transitions happen in each statement of the program. And all of this without having to spray printf statements in practically every line of your code. I'm always happy to get on my soapbox about this, but perhaps instead I should pitch this as a desperate plea to you. Please, take 15 to 30 minutes to go through the tutorial from precept again, and then maybe another half hour to replicate the tutorial with another program, maybe a slightly more complex one. The hour you take legitimately will save you tens of hours in this term on debugging alone, and that's before even considering the time spent waiting in office hours or lab TA queues on a bug that you could have found yourself. Again, that's not to say that you shouldn't come seek help. You absolutely should do that. But you can also make the most of that help by being prepared with the tools that we'll want you to use to get to the bottom of it. And if you're prepared to use them with us, you likely can solve a lot of your problems by using them independently. The second set of debugging suggestions for this lecture pertain specifically to dynamic memory. 2 weeks ago in Precept 9, you worked on debugging dynamic memory, but since Assignment 3 is coming up and that will be your first foray into actually writing code that dynamically allocates memory, it's worth your time to cover this in both Precept and lecture. With dynamic memory, a large number of bugs come back to a relatively small number of core ideas and their variants. This follows from the small number of primitives, or I like to think of them as ingredients, that we know about in dynamic memory, and an even smaller number of categories, or recipes, to extend the analogy, of errors within them. You can refer back to Precept 8 for the ingredients, malic, calic, realloc, and free, or the pointer dereference also sort of fits in here as another ingredient. And that's just about everything that can go wrong. Those functions, pointer dereferences, that's about it. And then you can refer back to Precept 9 for the recipes, that is how things go wrong. Dereferencing a dangling pointer, accessing memory out of bounds, creating a memory leak, or double freeing. So here are 3 common bugs we might find in code that uses dynamic memory. Take a moment to go on another bug hunt. Again, it's much better than just hand-waving at a line and saying, yeah, that's the part that's wrong, to be thorough, as though you were collecting evidence. So what's the ingredient that's misused? What's the recipe of how it's misused? And then the 3 other items that we were already talking about. When does the bug manifest? What's the effect of the bug? And how could we fix it? For number 1, the ingredient is a dereference. The recipe is a dereference of a dangling pointer specifically. The pointer value is never initialized, so even worse than pointing at something that used to be allocated, instead it points to just an arbitrary location in memory based on whatever value happened to be in memory at the location the pointer is now. So the result is either an inadvertent change to your program's data, or a segfault if it happens to point somewhere that you can't access. Number 2 is similar. It's more subtle because we don't see an asterisk to do an explicit dereference, but we call a function that will dereference our pointer. So it's still the dereference of a dangling pointer and still has that inadvertent change to your program's data or a segfault. For number 3, now we have a few more ingredients in play. The malic looks good, allocating enough room for exactly 1 int, and the dereference itself looks good. We're sticking 5 into the new allocation. But what happens if the allocation failed? We don't ever check if malic succeeded, and so if it failed, we're dereferencing a null pointer and we segfault. The free looks good, but then we dereference a dangling pointer that's still pointing to the memory that we just freed. This is, again, likely an inadvertent change, but there's some chance that, that the memory is no longer accessible to our program. Again, a problem either way. Here are 2 more. Again, pause to ascertain the ingredients, the recipe, the manifestation, and the fix. The first malloc looks great. The pointer dereference seems fine, but the second malloc is the problem. Pointing P at a new allocation without having first freed the old one is a memory leak. We've created garbage. That is, we don't have any way to reference the memory returned from the first malloc. And in the second, the malloc again seems fine, the pointer dereference looks good, and the first free is perfect. But the fact that I just said first free means there's a second, and we can't re-free a pointer that's already been freed. Double frees corrupt the heap, making all subsequent dynamic memory operations potentially incorrect, and in many cases eventually crashing the program when the runtime system realizes there's a problem and aborts the program. When students of C first get into pointers, and particularly dynamic memory, they're prone to make mistakes that lead to segmentation violations, or segfaults. This is where we dereference a pointer that's pointing at memory that the program doesn't have access to. It's natural to see segfaults as some sort of disaster. It's an error that terminates the program. Oh no! But I promise you that segfaults are a good thing, both because they give you a really straightforward way to debug the underlying issue, but also because it absolutely beats the alternative, where the program just goes about reading and writing to the wrong places in memory silently, digging further and further down into its own grave, until either it crashes for another reason or returns the wrong output. In both cases, it leaves the developer absolutely no clue as to where to begin to debug. With a segfault, on the other hand, you know exactly where to begin. In office hours in assignment 2, probably the second most common issue I help people with was segfaults. And it seems that many have missed the message that segfaults can help you see exactly where your problem is. So let me evangelize to the world. GDB can pinpoint the exact point in your program where the segfault occurred and give you an entire stack trace of function calls that got you up to that point. Simply compile your program with the -g flag in GCC, open GDB, run the program using the run command, and allow the segfault to occur. Yeah, that's right, let your program crash. After your program has died its ignominious death, issue the where command, WHERE, to see the location and trajectory of how it got there. While the line it dies on probably isn't where the error is, the line where it dies will show you the pointer that was in play, and thus the pointer that is the problem. Now you can play detective and walk back how that pointer's value got to be what it is. The backtrace and that's given back from the where command is helpful with this, of figuring out how it got there. You can find then, in that stack trace, in that walking back of where that pointer has been used, what happened to it. What is the problematic code? Is it a bad assignment to the pointer? Is it a loop sustaining condition that was incorrect, allowing us to walk off the end of an array? Is it a bad allocation that didn't allocate the right amount of memory, etc.? So speaking of bad mallocs that don't allocate enough space, let's see a few ways we can diagnose these problems. The first is by manual inspection. Use your IDE's search tool or the standard Linux tool to grep and find all instances of malic, callic, realloc in your program, and then go look at them. Make sure they're allocating the right amount of memory that your program is later on going to assume that they've allocated. Of course, if this is the issue, then you just wrote the bug in the first place, so it's possible that either through misunderstanding or lack of attention, you'll reenact that same mistake of writing the bug in your double checking. Nevertheless, it is oftentimes just a new read-over with fresh eyes that will catch these bugs. A very common error for some calls of malloc is to request too few bytes of memory. Here are 4 such malloc errors, so pause the video and see if you can identify what exactly the bug is in each and how they should be fixed. The first allocates one too few bytes because it misses the space required for the null byte that's not accounted for in the return from strlen. I know we've seen this on the slides before, but it's such a common error that I'm going to continue reinforcing it. The second doesn't allocate enough memory because size of S1 is always 8. That's too few bytes for the string hello world, which consumes 13 bytes. In the third, size of long double star is 8, because all pointers are of size 8 on ArmLab. But a long double consumes 16 bytes on ArmLab. This is a common error in assignment 3, and it's the first thing I always look at in office hours. The type of the pointer should be one more pointery. It should have one more star than the type and the size of in the allocation. The fourth is actually exactly the same as the third, just with a variable of the type long double star instead of the type name. Note though that star p would be fine, since the type that long double star points to is a long double. If you've gone back over and over and over and stared at your mallocs and you're convinced they're right, but your bug persists, another option is to change each allocation to allocate a hard-coded amount of memory, rather than the program-specific value you've initially written. If you change every malloc to request some large number of bytes, larger than any reasonable amount your program would ever actually request, now it's likely that you've changed whatever malloc it was that was requesting too few bytes. So when you run the program, If that was the case, your error will have disappeared. You're no longer malicking too few bytes. Now you just have to restore them one by one until the error resurfaces, at which point you know which is your problem child. This is time consuming because it's manually editing potentially many lines of code. When I say editing a line of code, you probably shouldn't edit the lines themselves. You should comment them out and put in a fresh malloc below them that has the hard-coded value. Otherwise, restoring it back to what it used to be is tricky because you don't necessarily remember what your original code said. But although this is time-consuming, it is often effective, particularly when you have something subtle that manual inspection misses over and over. Here you can go and pinpoint which one it is. The danger, though, is if this wasn't your bug, you've just wasted sort of a lot of time in changing everything to malloc way too much space and then having to go back and put it all back that was actually not your bug. A similar technique can be applied to free. If your program is crashing with a double free, a good technique is to take out all your calls to free. After all, you can't have a double free if you don't free at all. The same applies if you suspect your error is due to accessing a dangling pointer, so you're accessing memory that's already been freed. If you take out your frees, it hasn't been freed, and so that's not an issue. The idea is the same as it was with malloc. You comment out all the frees, see if the bug disappears. If it does, then incrementally restore each until you find the one that reintroduces the bug. Again, this is time consuming, but when manual inspection doesn't cut it, it's useful. And manual inspection is harder with free, since it's common for all of the free calls to be detached in both execution time and code location from the malloc calls. We don't often malloc something, use it for 2 lines, and then immediately free it. They might be in different functions and might be the entire runtime of the program separated from each other. Finally, the last technique that I'll mention just briefly is to use a memory profiling tool like meminfo or Valgrind. These tools intercept your program's memory allocation calls and keep track of what they did and where. This information can then be used to see if, for instance, the program allocated memory and then never did a free on that memory that it allocated. Meminfo was written by Princeton faculty member Bob Dondero and R.J. Lilstrom, class of 08, specifically for 217. Valgrind, on the other hand, is free, both in the sense of free as in speech and free as in beer. It's a free tool that is widely used in both research and industry. As you might suspect from that, that means Valgrind is more powerful, but it's also more complex and not really targeted at novice C programmers, whereas meminfo is simpler and more tuned into this class. In your assignments, we'll require that you demonstrate a clean meminfo report, so that shows that you have no memory leaks and you didn't corrupt the heap. But I do encourage you, when you get something that appears to be a memory management error, to try out Valgrind while you're trying to track down the bug. It has some fantastically detailed memory error detection that actually runs as your program is running. It's not a post hoc tool. It also looks at not just memory leaks and heap corruption, but also for multiple frees and for dereferences of dangling pointers. So that's it for this lecture. I trust that you'll make good use of these techniques in Assignment 3. But before then, I hope that you have a productive time studying for your midterm in this class and, of course, your midterms in your other courses. And after that, I wish you good luck on the exams themselves. And after that, I wish you a relaxing and rejuvenating fall break. I'll see you after that.